Okay, so thanks a lot for recalling. Good afternoon to everybody, and we are in this chapter which is on planar graphs. And let me recall, even if we have always drawn graphs, they are algebraic combinatorial structures, meaning the datum of a set of vertices, a set of edges, whatever they are, and a map sending edges to unordered pairs of vertices, okay? That's all which a graph is. Anyway, we draw graphs by points representing vertices, curve arcs representing edges which join actually the points representing vertices. And what happens is that sometimes we can draw these diagrams of the graphs we are interested in such a way that the arcs representing edges just intersect at the vertices, and that is the case of planar graphs. And what we draw is what is called, now we will see, a plane graph, meaning a graph whose vertices are points in the plane, whose edges are arcs in the plane, which do not intersect in the intermediate points. Okay, and so a planar graph is what? A graph in the abstract sense, the datum of V, E, and psi, such that a plane graph exists isomorphic to it, meaning it is possible to draw that graph with the diagram with no spurious intersections, okay? So there is a difference between a plane graph, which is already something which is drawn on the plane without intersections apart from the vertices, and the plane graph, which is a combinatorial structure for which such a plane embedding exists. Okay, we therefore sometimes refer to a planar embedding of a planar graph as a plane graph. Okay, so here we have a planar graph in the sense that there exists a plane graph, which is this, isomorphic to it. This is a plane graph, and this is not a plane graph. Why? Because here we have a good embedding in the sense that we have no intersections of these line arcs except at the points representing vertices. Okay, whereas here we have, okay, it's all right. We have so many times drawn graphs in this way just by spotting vertices and pointing them out like this with the circles or with big dots, whatever, and ignored these intersections. That's all right, okay. But there is a difference. There might be an interest in knowing whether it is possible or not to draw a diagram of a graph in this way, okay? So this is a planar graph because there is a morphic graph, which is this, which is plane embedded in the plane. So because there is a plane graph, this, which is isomorphic to it, okay? And so, for instance, we might have that that this is a certain graph where vertices represent Facebook users and edges represent friendships, as in our first examples, okay? And in this case, it is of no use to know whether you can embed that graph or not in the plane. In some other situations, it is important. Very easy situation, you have a complicated circuit not a circuit, but a motherboard, where the design of a motherboard, okay, and so you have points to be connected with each other through metal bands, okay? Is it possible to do it on a plain piece, actually without bridges? That is important for printed circuits, okay? Or how many bridges do you need, such things. So there are situations in which you are interested in that possibility. So this chapter is entirely devoted to this problem. There is a very beautiful answer to this problem, Kuratowski's theorem, which tells us when and only when a graph is representable on the plane, so when it is planar, but there are quite a lot of interesting things about planar graphs. Okay. This is the chapter which gives us an interplay between combinatorics, pure combinatorics, which was what we did so far, okay, and a part, I would say, of geometry, which is called topology, which is that part of geometry which is interested in something which is not metric, but just in the reciprocal position of points and lines in a plane, okay? And the first relevant thing is what is called a Jordan curve. It's a continuous non-self-intersecting curve whose origin and terminus coincide. And I just mentioned something which was puzzling more or less a bit more than 1 century ago. The fact that Jordan curve does something to the plane which is very intuitive at first sight, but rather difficult to actually prove. If you have in the plane a Jordan curve, which I repeat is this, where is it? A continuous, non-self-intersecting curve whose origin and terminus coincide, okay? Then, if you take away that curve from the plane, the rest of the plane is partitioned into two disjoint open sets. One is called the interior, and it is bounded, meaning that there is, if you want a rectangular box containing it, and an exterior of that curve, which is not bounded. There is no box which bounds it, okay? And they say this theorem is intuitively obvious, but the formal proof of it is quite difficult. And let me give a hint of this. So, oh. Sorry. Okay, this is a Jordan curve, and it is important, for instance, for graphics to have that there is an interior and an exterior of it, because, sorry, I must do it properly. Okay, more or less. Okay, at least because you have, I don't have that tool here, but in general you have the tool of filling, okay? And so that there is an interior and an exterior is very important for the filling tool that you have in drawing programs, okay? And it is important for many things in this chapter, but I'm not using this theorem, which is interesting for at least for this fact that it is very intuitive, but is difficult to prove that there is an exterior and interior, and that if you have a point in the interior and a point in the exterior, if you draw a line joining them, you must cross the curve itself. So how could it not be so? Okay, but try to prove it, all right? It is absolutely not easy. And many things well, what's happening now? Okay. Any line joining a point in the interior to a point in the exterior must meet the curve in some point, okay? I'm not using this. Here you see here you see that this theorem K5 is non-planar and K33 is non-planar. They are proved by using this Jordan theorem, but I prefer there is an alternative proof later, and I use that other proof. Anyway, just to let you know that there is something interesting also in the arrangement of points in a plane in a surface, in particular in a sphere. Yes, here there is the mention of something which is a whole thing which occupies books and books and books. The idea of what is a two-dimensional manifold, and this is something which has locally the same structure of a plane, but just locally. If you take a lifesaver, what is in geometry is called a torus. Now I want to see how I can. Torus is something of this shape, if you see what I mean. This is also a two-dimensional manifold in the sense that if you pick up any point, there is a neighborhood of that point which is in bijection bicontinuous correspondence with a certain open set of R2. And this is true for any point here in this object, okay? So this fact of being locally Euclidean, locally with the local model taken in R something, which will always be the same exponent, is what tells us this is what we call a two-dimensional manifold, okay? Actually, at each instant will live in manifold, meaning that in this room or the room in which you are all around the world in this moment, that is an open set in your space, in our space, which is by continuous correspondence, meaning a function which is continuous with continuous inverse, with what? With the piece of R3. We have absolutely no certainty, and actually some evidence that this space in which we live instant by instant is actually a three-dimensional Euclidean space. It is so just locally at each point, apart from black holes, in each point of our space, instant by instant, we can have around each point um, a open neighborhood, which is we call it homeomorphic, which means by continuous bijection with an open set of R3. So instant by instant we live in a three-dimensional manifold, and if we take also time into account, so around each point at an instant of time, we are in a four-dimensional manifold, meaning that if we take also time as a fourth coordinate, then for each event, which is a point, comma, an instant of time, we have around that event, we have a neighborhood which is by continuous correspondence with an open set of R4. So space-time is a four-dimensional manifold, and instant by instant space is a three-dimensional manifold. Black holes excluded. I don't know how to get rid of this. This is new. No, I must do it like this and do it. Okay. And so there is, of course, mathematicians don't stop to reasonable things, but always go beyond. So the problem, is this graph embeddable in the plane? Is it embeddable in the sphere? We'll see in a moment that the two problems are exactly the same. And then, is a certain graph embeddable instead in the torus? Is it embeddable in the Möbius band, in a cylinder, and so on and so forth? Okay? All right. And for instance, we'll see that K5, the complete graph with 5 vertices, is not embeddable in the plane, but as you can see here, it is actually embeddable in the torus. Okay, this is actually K5. Each of the 5 vertices is joined to each other of the 5 vertices, and you can embed it going here around the hole and here around the handle, how to say, so to say, in this way, okay? And what about K33? The problem I exposed to you a very long time ago, meaning we have 3 neighbors and the 3 shops, and they want to build roads from each of the houses to each of the shops, but they don't want to intersect the streets in the middle. Is that possible? We'll see that it's not possible. K33, the complete bipartite graph with 3 and 3 vertices, is not planar, but as you can see here, it is embeddable in what is called a Möbius band or Möbius strip, which is what you can get by yourself by taking a belt, doing half a twist, not an entire twist, but half a twist of the belt, and then closing it, and you get this, which is called a Möbius strip, okay? And this is an embedding of K33, the complete bipartite graph on 3 and 3 vertices in the Möbius strip, okay? Now, this fact that I was hinting before, that embeddable in the sphere, on the sphere, and embeddable on the plane are the same. Why? Because we have this, which is called stereographic projection, okay? The stereographic projection goes like this. Place a sphere on a plane, touching it by just one point, okay? A ball on a table, okay? But an infinite table, actually a plane, not just a piece of plane, okay? And then call North Pole, place it with the South Pole on the table and take the North Pole, okay? From the North Pole, draw half lines, okay? Half lines which cut the sphere. Oh, sorry, again, I was forgetting. In mathematics, at least in the last few tens of years, we call sphere the spherical surface. And for the solid, we say ball, okay? I know that you are used to call sphere actually a solid. Okay, but let me adhere to what we do generally in geometry. So sphere is the spherical surface. Ball is the solid bounded by the sphere. Okay, so we cut the sphere in a point, but we also cut the plane in a point. And this gives us a bijection, which is not just a bijection, but a bicontinuous bijection, meaning that if I send this point of the sphere to this point of the plane, this is a continuous map. And if I go the other way around, coming from a point of the plane through the half line connecting it to the North Pole and cut the sphere in a point, this also, which is the inverse function, is continuous. So it is a bicontinuous application map. From what to what? From the sphere except for the North Pole. Okay, so not all of the sphere, but the sphere from which we have taken away has no corresponding point in the plane. All other points of the sphere have a corresponding point in the plane. Okay, and so from sphere minus North Pole to the plane. Okay. And this is nice. This is what I wanted to play a little bit with, if I can. Let me see whether I can do that. Oh, just a moment. Oh, yes, but okay. Can you hear me anyway?
Yes.
Okay. You can find this and some other demos on the list which I have put in the program page, okay? If you go to the program page in my website, okay, you find that there is a link to a list of demos, and you just have to download a player, okay, which I cannot do on the main computer here in the classroom because I've not the rights of the administrator, but I have on my laptop, and it's completely free, and then you have access to thousands of very interesting programs made by users of a certain commercial application. And this is a very nice one, showing you the this projection, okay, which you can explore also like this, and you can change the thing to be shown. Okay, just to have an idea of what this stereographic projection does, okay? This with the square is maybe the most interesting for us, okay? And you can see that as we approach the North Pole here, the image on the plane goes away from the tangency point, okay? Goes towards infinity, so to say, all right? And so while we go, if we take a point and try to go towards the North Pole, then that point goes away towards infinity. In each possible direction, it goes towards infinity. Okay, that's all I wanted to show you, so I can come back now. To here our thing. Okay. Okay, so this is this stereographic projection. And so what happens is that if you have that you have a certain plane graph, you also can have an isomorphic graph drawn on the sphere without self-intersections. And conversely, if you have a graph which is drawn on the sphere, you can, of course, avoid passing through the North Pole, okay? So, if you pass through the North Pole with an edge or a vertex, you can just roll a little bit the sphere so that the North Pole is free, is not belonging to an arc or an edge or a vertex of the drawn graph, and so your graph, which is drawn on the sphere, has an isomorphic graph drawn on the plane. So all graphs which are planar are also embeddable into the sphere, and conversely, okay? And this is theorem 9.2, okay? Try this. Find a plane embedding of K5 minus one edge, of K33 minus one edge, any edge, okay?
This is graph, sir.
Pardon me?
Would you please share your desktop? It is disconnected. Yeah.
Oh, sorry. No, it should be shared.
Thank you.
Can't you see the the book?
We can see the book.
Can you speak yes or no?
No.
Or maybe I just have to get away from here. And now?
Yes, now
Yes, Professor.
Sorry, it was the use of the laptop at the same time. Okay, so this is the drawing I was referring to, okay? A graph on the sphere, just taking care that no edge, no vertex goes through the North Pole. Then you have that an isomorphic graph is embedded in the plane. A graph embedded in the plane, and you can get a graph embedded in the sphere. So you have what is here. A graph is embeddable in the plane if and only if it is embeddable on the sphere. Okay? And now this easy exercise, find plane embeddings of K5 minus 1 edge or K33 minus 1 edge. Now, when we have a plane graph, then we have faces. Okay, what do we mean? If we mean this, that if we take out of the plane the points representing vertices and the curves representing edges, then we are left with some pieces of plane, okay? These pieces are called the faces of the plane graph, okay? One of these faces is unbounded, and it is called the exterior face. So 9,6 is here. This is a plane graph, and the faces are F1, which is all around here, okay? And this is the exterior, unbounded face. And then you have what? Where is F2? F2 is this quadrilateral face. F3 is this, which is triangular, if you want to call triangular such a thing, okay? And then F4, okay, between these two parallel edges. Be careful, this F5 is also without a hole. Why? Because we take away this edge, so it opens up, okay? I mean that this face F5, this face F5 is okay, it's like this. Why? Because we delete, we take away from the plane all this, and so our face is all this one, okay? And so it is also deformable into a square, into a disk, okay? Okay, so and we call F, capital F of G, the set of faces, and phi, this is Greek letter phi of G, the number of faces of the plane graph, okay? As I said, if you have exactly one unbounded face, okay, called the exterior face. Now an interesting thing which could look a bit puzzling. Let V be any vertex of a planar graph G. Then G can be embedded in the plane in such a way that V is on the exterior face of the embedding. I read what is written here and then try to draw something to let you understand what happens. Consider an embedding G tilde of G on the sphere. Such an embedding exists because of what we have seen with embeddable in the plane equals embeddable in the sphere. Let Z be a point in the interior of some face containing V, and let pi or G tilde be the image of G tilde under stereographic projection from Z. Then this is a planar embedding of G of the desired type. Now I try to draw that, okay? So it's not easy. So we have the sphere here with our north pole here. Okay, it is like this. Here we have the plane. And what? We have, say, a certain graph and this is vertex V, all right? So if we take it back, let me call just A, this vertex here. Then if we take it back to the sphere by a projection, by stereographic projection, we have something like this on the sphere. All right? Can you see what I mean? We have these rays going through, and that's difficult for me. Okay, no, forget it. Let me do it again. No. Very ugly. Okay, so you have here a certain graph, and you have that a certain vertex V is here, not on the exterior face. It is on one of the interior, three interior faces, okay? And here you have that the exterior face of this plane graph corresponds to all this big part of the sphere, the one which contains our North Pole. All right? But now what can we do? We can roll the sphere. I'll do it in the next page. So that the North Pole is now inside the triangle Okay, so we have just rolled the sphere with respect to the previous. This here, the triangle was here. Now I rolled the sphere so that now the North Pole is inside the triangle. Okay, and so now if I project, I will get that this becomes the exterior face. So you have a very big triangle here. It's not possible to draw it here because it's very large now, since they are so close to the North Pole, these points. But now the V is on the exterior face. Let me deform it a little bit. And so we have that we'll have here V, and then we'll have this, and this, and this. And this, it will be here. We'll have that it goes like this and it goes like this. Okay. Okay, so V now is on the exterior face. All right, so all right. Okay, now we have the boundary of a face which we call B of that face F. Okay, we have a face F, we denote the boundary as B of F. Then we can see it as a closed walk in which each cut edge is traversed twice. Let's see here. If we take the face we saw before, the one I have drawn by itself, okay? Then its boundary, let's start with something very easy, this face F2. Then its boundary can be seen as a walk E1, E3, E4, E5, and we are back here, okay? As for F3, its boundary can be seen as E3, E2, E4, and we are back here. Here things are a little bit more complicated. I can, for F5, I can go E9, E10, be careful, E11, E12, again E11, and that's because E11 is a cut edge, and then E8 and coming back to the original vertex. So whenever I have a cut edge, this is gone through twice, once in a sense, the other time in the other direction, okay? Look, from V6 to V7, from V7 to V5, from V5 to V8, then E12. Now from V8 to V5, and then from V5 to V6, okay? And also here, this is also true for F1, the exterior face, okay? Here we have another cut edge, and so we can go around the boundary of F1 in this way. E9, E10, E6 from V5 to V4, E1, E2, E5, E6 from V4 to V5, and then E7. Where did I start? Here or? Okay, so now we close, okay? And we get this closed walk in which we go through the same edge twice, if and only if in the graph it is a cut edge, okay? When B of F contains no cut edges, then it is a cycle, meaning that you go through each edge and through each vertex just once, apart from origin and terminus, which coincide, okay? And you can here have two examples. We have already seen some. A face F is said to be incident with the vertices and edges in its boundary. If E is a cut edge in a plane graph, just one face is incident with E. On both sides, you have the same face. This is true here. On both sides of E11, you have F5. On both sides of E6, you have F1. This is important for something we'll do later. Okay? If E, just one face is incident with E, otherwise, when you have something, an edge which is not a cut edge, this also for loops, as we can see in the example above, there are two faces incident with E. Even for this loop, we have two faces incident with E12, which is a loop, F5 and F6, okay? Of course, a loop cannot be a cut edge. Okay, we say that an edge separates the faces incident with it. The degree of a face is the number of edges with which it is incident. But remember that you count twice cut edges, if any, okay? The number of edges in B of F, but cut edges being counted twice. Why? Because when you go around the boundary, you meet it twice, okay? So the degree counts twice the cut edges possibly present in the boundary. And okay, F1 is incident with, look at the picture and you see, for instance, E1 separates F1 from F2. What is it? E1, okay, where is E1? F1 from E2, from F1 from F2. E11 separates F5 from itself, okay? Actually, it joins, if you want, F5 with itself. Okay, Given a graph, a plane graph, not any graph, but a plane graph, and not even a planar graph. This is a mistake some authors do, not these ones. Given a plane graph, you can define what is called the dual graph, G star, as follows. Corresponding to each face F, there is a vertex which we can call F star of this new graph, and corresponding to each edge E, there is an edge E star or G star. Two vertices, F star and G star. What does that mean, two vertices, F star and G star? Two vertices corresponding to two faces of the original plane graph are joined by the edge E star if and only if the corresponding faces F and G are separated by edge E. Okay? The graph G star is called the dual of G. A plane graph and its dual are shown here. Okay? Here you have a plane graph, and then for each face you have here a vertex. Okay? You have face F1, which is represented by this vertex F1 star. Then how come do we have here a loop? Why? Because there is this edge E8 which separates F1 from itself. It is a cut edge, okay? And so F1 is is adjacent to itself through E8, and so vertex F1 star is adjacent to itself through E8 star, which here is a loop. You have a loop for each cut edge in the original plane graph, okay? And, okay, you can see, for instance, F1 and F2 are separated by edge E1, so F1 and the F1 star and the F2 star are joined by E1 star. But look, there is also an E2 star. Why? Because also F1 and F2 also have another edge separating them, which is E2. And so there is an edge E2 star joining F1 star with F2 star. Okay? But there is a nice thing, and this is that you can actually easily draw one upon the other by thinking, as was at the beginning, by thinking of these as regions in a political map and picking up the capital town here in each of the regions and joining them for each edge of the boundary by an edge. Okay, and so here you can draw one upon the other. All right? And there is a nice thing that if you draw in this way and do the dual of the dual, you come back to the original plane graph, apart from moving it a little bit, okay, deforming it, but surely a graph which is isomorphic to the original one. Okay? It's easy to see that the dual G star of a plane graph is planar. In fact, there is a natural way to embed G star in the plane, and it is what we have just seen. We place each vertex F star in the corresponding face F of G, and then draw each edge G star in such a way that it crosses the corresponding edge E in of G exactly once, and crosses no other edge of G. Okay? And it is intuitively clear that we can always draw the dual as a plane graph in this way, but it should be proved. And note that if E is a loop of G, then E star is a cut edge of G, and if E is a cut edge of G, then E star is a loop in G star. Okay? We define it abstractly, but since we can draw it in this very easy way, then it is sometimes convenient to regard the dual G star of a plane graph as a plane graph itself. This is embedded in the way we have just seen. And then we can consider the dual G star star of G star, and then you can see that G star star is isomorphic to G. Okay. What is interesting is that isomorphic plane graphs may have non-isomorphic duals. So the dual is not related to a planar graph as an abstract structure, but to a plane graph, something which is already embedded in the plane. And this is given in figure 9.A. 8.8, where is it? Here. You can find an isomorphism between these two. That means that you can put names here, A, B, C, and here A prime, B prime, C prime, and so that if A and B are joined by an edge here, E prime and B prime are joined by an edge here, okay? Find by yourself these isomorphism. It's actually very easy. You can take this inside, okay? Can you see that? To find the isomorphism. Oh, I'll do it, okay? Let me have it here, as was the very easy suggestion. Oh no, I should remember that. Come on. All right. Okay. And so you can see that they are actually isomorphic. I don't put names on the edges, but you can if you want, and see anyway what is important, so that if two vertices are joined here, the corresponding ones are joined here, and vice versa, and conversely, okay? So these two are isomorphic, but their duals are not isomorphic, and I can see that by the fact that here I have a region of degree 4, okay, whereas here there is no region of degree 4. Degree meaning the number of edges in the boundary of it, okay? So naturally these two, the two dual graphs of this and this plane graphs are not isomorphic, okay? But if you want, you can find the non-isomorphism by just doing this, okay? And so on and so forth, and here, here, and so on, okay? You can build the two duals and see that they are not isomorphic, and you discover that just by looking at the degrees. Here you will find a vertex of degree 4, and here you will find no vertex of degree 4. And so, of course, the duals are not isomorphic. I can't understand what I should do here. I'm sorry. This is a new thing. Okay. 520. Okay, let's see this. 9.4, theorem 9.4. If G is a plane graph, then the sum of the degrees of the faces is equal to twice the number of edges. And that's fairly easy. Why? Because the sum of the degrees of the faces is the sum of the degrees of the vertices of the dual. Each vertex corresponds to a face. Each vertex with the star corresponds to a face. The degree of the vertex is the number of edges coming to that, incident to that vertex, which is the number of edges around that face, okay? But this is twice the number of edges of G star, because this is the sum of the degrees of the vertices of the dual, so it's twice the number of edges of the dual. But we have an edge of the dual for each edge of G, and so this is twice the number of edges of G. And so we have this, which will be used. Okay. And now we go to Euler's formula, but this is so important that we make a break before. So it's 521, let's say 522. We make a break now, and we start again at 532.
When they are going to be sent the result of the midterm.
Sorry?
For the result of the midterm.
The results of the midterm will be, I hope, either tomorrow night or the day after tomorrow, will be in my web page, and so you can go through virtuale.univo.it to there, and you'll find also the solutions, actually not just the outcome, but your marked essays. Okay, so I'll take your essays and mark them directly. I don't give explanations when marking, but you can then see the solutions I give. Okay. For the solutions, I don't give a particular derivation of neither of the number of spanning trees nor of the chromatic polynomial, because it would be just one of the many possible, okay? And there I just give the result. What I hope you didn't do, I hope you did give me all the procedure, okay? There, for those two, I'll just give the number and the polynomial, okay? Anyway, you see everything. You can go to it through Virtuale or directly through my web page, okay? So it's 24, let's say 25. I start again at 35.